So here we use the MBSE approach from the beginning. This was driven by Airbus Defence and Space. Just to describe the dynamic behavior, they used primarily MATLAB and Simulink. The physical architecture was described in effectively a spreadsheet. And for the functional architecture, they used SysML. The functional decomposition and system interfaces were also defined in SysML. And so our job was to link SysML with simulation. And we did this using the MBSE pack that we just looked at. So we worked together with them in Roma to link SysML, their SysML model, with their simulation tools. And this gave them ability to accurately estimate mission performance at this early phase level. And now we're continuing work with them to do some exploration to find optimal designs to see if their nominal design will survive all the possibilities that it might encounter. For example, the thing that are varying is the spin of the target. They know the current spin, but by the time that the mission is launched, they don't know the spin. It will be at the spin rate. Okay. This is a demo of the simulation done in STK of the actual rendezvous. So here we see the chaser approach the target, which is spinning. It will now find the axis of rotation, come in, match the spin, and then climb onto it. All fully automated. And a big concern here is safety. So more important than the success of the mission is safety. The last thing they want to do is actually crash into the target and create the space debris that they're trying to avoid. So part of this is quite a novel trajectory that as they approach the target, if there is a failure at any point, there's little risk of hitting the target. So here I'm going to show you a video of the actual model simulation. Let me go back to the actual video. Okay. So, as before here, we're in a MBSE world, in Magic Draw again, and we have our system definition. And what we just did there is to, the study here is to try different batteries. So we have a catalog of different batteries, and for a particular battery, we want to see if the mission is successful. The mission is actually based around this state diagram, or the mission simulation. There is the FAR approach, where we get close to the target. Once we get close enough, the guidance changes and it enters an automated mode, so that's the near approach. At any point we could have a failure and the chaser returns to a reset point far away and tries again. So here this is represented by a far mode, a near mode, and then a collision avoidance maneuver, the recovery mode. So we come here, we could go there, then come back here, and then exit the mission here. At the same time, we have have the state of the instruments, which also changes depending on which mode we're in. So I'll show you the simulation running here. And in the background, again, we have a model center evaluating the actual state of the mission. So here we can see we're in near approach. And here we can see model center is making some calculations. And it time steps through the mission. At some point, we enter the near mode. There's a failure. We go back to far, and then we step through the near again, and finally finish. Okay. So here we finish, and we have this data. Okay, we see the final state of the mission and whether we've met requirements or not. We can also then plot what happens in the mission throughout the whole thing. So let me explain what we have here. So in this mission, you can see some sections. The first was the far approach. And the main thing we're looking at is if we have enough power during the mission. The power is coming from the battery, but is also regenerated by the solar panels. At the far mode, our load on the battery is low because we're not using the visual guidance instruments. So you can see that the battery here stays full. We then enter the near mode, and we can see that the available power starts dropping. We have then a failure, which means we go back to the far mode. So here we've got excess power from the solar panels because our consumption is low, and our battery recharges. Then we enter the near mode and complete the mission successful. And you can see our power goes down but never goes to zero. So you can see, for this case, that the battery was big enough. So this is kind of a simple case, but it illustrates what kind of studies Airbus can now do with their mission. And remember, this is still at very preliminary stages, at systems level. Okay. So what I just showed you was a simplified example for demo purposes, but in reality their mission is more complex. There's a lot more time steps. Right now for that part of the mission, it's something like 1,100 time steps. Here they're looking at, I think, again, power and the angles of the solar panels related to the sun. There's an SDK in the background which is providing this information. But this is what they didn't have before. They couldn't visualize what happens to all the systems, all parts of the spacecraft throughout the mission. And so now we continue the work to build on top of what we've done already. And so we're entering the design exploration part. And just a few words about the general approach. We have, let's say, the design space that's defined by all the possibilities. First, we want to narrow this search. And I won't go into details here, but This is things like realizing that a particular parameter, only a small range of it actually gives you good results. So the initial study identifies which parameters, which ranges are interesting. Some parameters may not be interesting at all, so you throw them out and reduce your search space. Once you've narrowed down your search, you want to do a good sampling of this, and you'll use design of experiment technology to do that. So then you'll use Model Center to basically to accurately sample the interesting part of the space. And this might be a couple of loops. Then once you have some interesting data, you will use visualization tools that we looked at before to analyze your results, and then use optimization, which again we saw, to automate the search. That's just a very high-level summary of the exploration strategy.